Today we will show how reservoir engineers use basic fluid mechanics and reservoir dynamics to derive and solve for flow rates within hydraulic fractures of perforations. This is important because with the industry the way it is, we are fracturing a lot of shell plays, and reservoir engineers routinely calculate flow rates in and out of these reservoirs. It is important that we analyze the flow through hydraulic fractures because they are specific to reservoir engineering and they are crucial in calculating flow rates for productions.
Here's some basics of fluid mechanics. The basic flows that we're dealing with are laminar and inertial flow. So, when looking at these flows, you have to include your Reynolds number. The Reynolds number is nothing but the density times the velocity times the length divided by the viscosity, which are your inertial forces divided by your viscous forces. In general, inside your piping, there's three types of basic flows. When your Reynolds number is less than 1, it's creeping flow, which is for all viscous forces. The mid-range dealing with the Reynolds number is laminar flow, which is mostly used in your reservoirs. And any large Reynolds number deals with turbulent flow. Laminar flow has low velocities, your fluid particles move in a straight path, and your Reynolds number is very low. In inertial flows, you have high velocities. The particles and the paths are completely irregular, and the Reynolds number is high. The Reynolds number is high, and it induces mixing of the fluid. So, what can we expect to see in these flow regimes? Flow inside a wellbore and inside fractures, we should expect to see inertial flow. Flow near the wellbore, you should expect to see inertial and laminar flow, which is a transitional phase. And inside the reservoir, it should be creeping flow, which is Darcy flow. Just to give everyone a basic understanding of what the fundamental principle dealing with reservoir dynamics is, you have to understand Darcy's law. Darcy's law is the basic equation used to describe laminar flow through a porous medium. It has since been derived into other formulas used for multiple flow scenarios, such as Nansen flow, multi-phase flow, and inertial flow with Forsheimer coefficients. The flow rate version of Darcy's law, most commonly used in petroleum engineering, is illustrated as Q being the flow rate, which equals permeability times the area multiplied by the difference in pressure divided by the viscosity of your fluid times the length of your pores.
In an attempt to increase productivity, hydraulic fracturing is being applied to lower permeability reservoirs. It's important that we're knowledgeable about non-Darcy flow effects because they play a crucial role in oil and gas production performance. Forsheimer proposed a general flow equation that took the nonlinear effect of turbulence into account by adding a second-order term into the original Darcy's law. As velocity decreases, as in laminar flow, the second part of the equation can be ignored, leaving the original Darcy's law. But as velocity increases, as in inertial flow, the second half of the equation must be taken into account because it has a very significant impact on the pressure gradient. The beta factor, also known as the Forsheimer coefficient, is characteristic of the porous medium being observed. It is usually determined experimentally from the slope of the Forsheimer graph. While investigating non-Darcy flow and hydraulically induced fractures, Cook suggested the following equation. And Lopez-Hernandez summarized many beta coefficient equations into a general expression where A, B, and C are different for each case. Here we show the Forsheimer equation that was presented to us in class. Jones, Blount, and Glaze used this equation to solve for yet another formula for the Forsheimer coefficient. It's a little easier to see what's happening in the equation if it's rewritten as average pressure minus pressure of formation equal to a coefficient A times Q plus coefficient B times Q squared. Then you can just use this quadratic equation to solve for your flow rate. Apparent permeability, as defined by Langland and Burgoyne, is the fictitious value of permeability which produces the equivalent behavior our flow rate in a system with the same total length and their same total drop in potential. The equation presented in 1965 by R.W. Parsons for overall apparent permeability and the direction of the pressure gradient is shown. It is apparent permeability equals length over height times horizontal width times flow rate times viscosity over your overall pressure gradient.
So in 2005 at the SBE Annual Technical Conference and Exhibition, J.L. Miskimans and H.G. Lopez Hernandez presented a model that shows non-Darcy flow effects within hydraulic fractures. The spreadsheet model was developed through Excel to observe the effects that the non-Darcy flow takes on given different flow rates and bottom hole pressures. They used the Forchheimer equation as a starting point and derived on from there and ended up with their model that gives a ratio of apparent permeability at various flow rates versus the Darcy permeability at very low flow rates where non-Darcy effects don't take place. Alright, the model is convenient because it accounts for characteristic length in the dimensionless Reynolds number, and it also gives off a minimum permeability plateau. So they designed the spreadsheet model in Excel to solely focus on the loss of flow capacity in the fracture and prop impact, disregarding any transient flow behavior or any other outside behaviors that could affect it. Calculations were presented at two bottom hole flowing conditions using two commonly used prop impact pack widths, 0.13 centimeters and 0.25 centimeters. The first bottom hole pressure conditions were 1000 psi and 90 degrees Fahrenheit. And what they observed is that the larger width decreases the superficial velocity, which overall decreases the amount of non-Darcy effects that take place within the flow. Yeah, what they found is the 0.13 centimeter pack experienced 17% decrease in retained permeability, while the 0.25 centimeters only had a 9% decrease, which is shown on the graphs. This upper darker line is with the non-Darcy flow. They're both calculated using the Forchheimer equation. This y-axis is a fraction of Darcy permeability remaining. So this lower line, the magenta colored, takes non-Darcy effects into consideration because of the velocity that was used. It has a much lower fraction of Darcy permeability remaining, which is also for the 0.25 centimeters. So both show the same thing, but 0.13 centimeter pack resulted in a higher reduction in permeability fraction. Alright, second bottom hole conditions at 4000 psi and 150 degrees show similar results. As you can see in the graphs, this magenta colored line, it still lies below. And so, in conclusion, all the plots show that the non-Darcy pressure losses result to a reduction in the flow capacity. And what it's just saying is that when you decrease the fracture width, it also decreases the permeability even more than it already would have decreased due to non-Darcy flow. In conclusion, reservoir engineers really need to take in these non-Darcy effects into consideration in order to receive accurate calculations for production reasons.